Okay, we can start. Good
Okay.
morning and evening, everyone. My name is Stanley Pokar, and I am the president of the SEG Student Chapter at the Central University of Ecuador. It is a pleasure to welcome you all to this lecture. It is an honor to welcome you, Dr. Hitzman, professor at the University College Dublin and director of the Irish Centre for Research in Applied Geoscience. Dr. Hitzman holds degrees in anthropology and geology from Dartmouth, a master from the University of Washington, and a PhD in geology from Stanford. He began his career at Chevron Resources, where he led the discovery of the Leaching zinc lead silver deposit in Ireland. He later worked in United States science policy roles, including the Senate and the White House, before becoming a professor at Colorado School of Mines. In 2016, he served as Associate Director for Energy and Minerals at the United States Geological Survey. He currently advises cobalt metals. We are pleased to have Dr. Hitzman with us today to share his expertise. To the attendees, if you have any questions during the presentation, please leave them in the chat and we will address them at the end. Thank you, Dr. Hitzman. We can start.
Thank you very much, and thank you for the invitation to talk to the student chapter there in Quito. I'm very pleased to be able to do this. As you'll see, the slides do have Spanish translations, so while I will speak in English, hopefully you'll be able to at least read some of the translations as I go through. So what I want to talk about today is the Irish zinc, lead, and copper ore field. And to talk about the ore field generally, it's been active. There's been active exploration for over 50 years. 15 deposits have been found with over 1 million tons of zinc and lead. And of those 15 deposits, 8 have been operated as mines, 6 as zinc mines, 1 barite mine, and 1 copper mine. And currently one of the former zinc mines is being readied for reopening. The Carboniferous Basin, which hosts the deposit, is relatively little deformed and the rocks are unmetamorphosed, enabling study of the tectonostratigraphic controls, the structural and lithologic characteristics, the original textures and mineralogy, and the fluid compositions of these deposits. And the ore forming processes are visible and can be studied in great detail, and in fact have over the last 40 years. So the Irish ore field, shown here, is in the middle of the island of Ireland. It's a relatively small place. As you can see, the ore field is about 80 kilometers wide and roughly 200 kilometers long. It ranges from, in the north, deposits that are hosted in the Pale Beds. I'll talk about that more, including the world-class Navan deposit, down to the south, southwest, a whole series of deposits hosted in the Walsortian limestone, with some of the further south deposits being the new copper deposits. So, some general characteristics. Deposits occur in the stratigraphically lowest non-argillaceous carbonate rock unit. The deposits are along or adjacent to normal faults at all the deposits, with the exception of the Palace Green or Tober-Malug deposit, which is still being evaluated, where major faults have not yet been found. The deposits range in morphology from stratiform to somewhat irregular, and the deposits are dominated by sphalerite and galena, but do have abundant iron sulfides, both pyrite and marcasite. Barite is commonly present. It can be either trace amounts or quite abundant, and in fact, in one deposit, it was dominantly barite and mined for barite. There's minor copper and silver-bearing sulfides, primarily chalcopyrite and tetrahedrite tennantite in many of the deposits, commonly in the feeder zones or actually in the fault zones where the fluids came up from below and intersected the carbonates above. So, paleogeography and stratigraphic control. Ireland, when the deposits were actually being formed, when the host rocks were being deposited, was at low latitudes in the tropics. And during that time, it obviously was in a tropical ocean with conditions that allowed for deposition of abundant carbonate rocks. Underneath the carbonates, the basement to this district is between two major cratons, Laurentia to the north, Avalonia to the south, and in between is a large group of different rocks, mainly Ordovician Silurian age, which formed in the Iapetus Ocean as a series of magmatic arcs and sedimentary basins, which were later intruded by a number of different plutonic rocks. If we look at these rocks, many of them are quartz-rich feldspathic greywackies with some volcanics, primarily basaltic, and chert and shale. The rocks have been metamorphosed from very low-grade Prainites pompilliite to green schist grade. And lead isotopes, which I'll talk about later, indicate that this low-grade metamorphic sequence is the primary metal source for the district. Okay, this is a north or south to north cross-section cartoon across the Irish Midlands. In the south, we have a thick basin of old red sandstone, Devonian in age, and going to the north, into the purple there, which is the basement rocks, we had a major transgression in the Carboniferous with lower limestone shale above the old red sandstone, so marginal marine deposits, which are interfingered to the north into younger Novan group, which are dominantly shallow water, siliciclastics, and carbonate rocks. Both these units are overlain by argillaceous carbonates or ramp sequence, the Ballystine limestone, which is then overlain by the Walsrosian limestone, which is called the reef, but is actually a deep water mudbank facies. And most of the deposits are in the south at the base of the Walsrosian limestone, and in the north in the Novan group. And in both these positions, these stratigraphic horizons represent the lowest clean or non-argillaceous carbonates in the local stratigraphic succession. Paleogeographically, in the Upper Devonian, when the Old Red was formed, Ireland, as you can see here, was a low area where rivers drained from areas to the north, between highlands, both to the east and the west, and draining to the south into an ocean. During the Lower Carboniferous, the sea level rose, ocean water, marine water came up and transgressed through the middle of Ireland, and this is the Irish Midlands Basin, as we call it now, with the carbonates. So the Old Red Sandstone is dominantly Upper Devonian in age, but parts of it reach into the lowermost Carboniferous. It ranges from conglomerates and sandstones to muddy siltstones, so going from terrestrial to marginal marine. The picture on the left actually shows a sequence of thinning upward beds, the lowermost being thick terrestrial conglomerates, and as we go up that mountain, going into thinner bedded sandstone bodies. As we move into the Lower Carboniferous, it's called the Corsaean. The paleogeography is as you see there. So to the south, South Munster Basin, which is where originally the Old Red was, is now a starved basin with marine shales, and we have marine waters have transgressed northward across the country, depositing a series of different limestone units. And in the south, the Carboniferous carbonates are conformable on the Old Red Sandstone. And as we move to the north, as we saw on the last slide, the Carboniferous carbonates are unconformably overlying the lower Paleozoic basement. The host rocks for the lead zinc deposits are predominantly the Walsrosian limestone in the south and the Novan group in the north. And I've shown where the deposits are actually located here with the red dots, and you can see it forms sort of a random pattern. There is a transition. In the south of the country, we have the lower limestone shales, and that's the south of that dotted orange line going across the country from Dublin to Galway. And to the north, we have the Novan group, which are mixed shallow water carbonate and siliciclastic rocks. The ore, as I said, the ore deposits here form basically a shotgun pattern on this map. So it's very hard to see what geologic control there might be, at least within the host rocks themselves. So let's look at the parts of the section that actually host the ore deposits. In the north, it's the Navan group. These rocks are also called the pale beds, and they represent the marine transgression in north-central Ireland. The Navan group consists of a mixed sequence of sandstones, shallow water carbonate rocks such as micrites, calcarenites, and oolites, with some very minor anhydrite-dominant evaporitic sediments. They show a very complex cement history prior to mineralization. So a lot of the rocks have been occluded, their porosity and permeability occluded during diagenesis. Overlying the Navan group is the Ballystine limestone, also called the ABL, or the argillaceous bioclastic limestone. It lies conformably above both the lower limestone shell in the south and the Navan beds in the north. It's composed of medium-bedded argillaceous calcarenites, and it serves as a regional aquiclude. As you can see on the upper left, you can see the bedded nature of these rocks, different variable thickness of the different carbonate beds. And on the lower right is drill core through these units. You can see the paler gray, more carbonate rich with all the little white specks, which are bioclast or fossils, and the dark gray, which are shaly intervals, which is what's making it an aquiclude. Above the ABL, or the Ballystine, is the Walsertian limestone. As I said, is often called the reef. It lies stratigraphically above the ABL. It represents deeper water deposition from tens of meters to probably over 200 meters in water depth, and it's carbonate mudbank sedimentation. So these are forming mounds on the sea floor. They are accumulations of biogenic material, but it's not a shallow water reef. The Walsertian mudbank consists of these micritic mudbank facies, and then between the mounds, the actual growing mounds of material, because of things like bryozoa, we have off-bank, more argillaceous facies, which actually are quite similar to the underlying Ballystine limestone. And cross-cutting relationships indicate the Walsertian limestones were lithified very early, within meters of the seafloor. So these things became essentially rigid, or rocks, with burial of less than a couple of meters. So if we go from the very lowermost Carboniferous, what's called the Corsaean, up to the next stage, which is called the Chaldean in this part of the world, there's a dramatic shift in the facies pattern. In the late Corsaean, we have layer cake type of transgressive stratigraphy right across the country. In the Chaldean, that breaks down into a whole series of different facies packages, which I call a facies mosaic, of both shallow water rocks, such as oolites and platform carbonates, and deeper water rocks, carbonate turbidites. And this facies mosaic is indicative of structural control of the facies. There's two major east-west trending troughs, the Dublin Basin in the northeast and the Shannon Basin, or Shannon Trough, in the southwest. They're probably related to relatively minor, sort of 10% extension, and also with a component of regional dextral shear. At the same time, we have initiation of limited basaltic volcanism, both in the Dublin Basin, shown by the pink dot, and just to the south of the Shannon Trough, shown by that pink oval. And if we look at where the ore deposits are now, the red dots, you can see that many of them actually line up along some of these troughs, which are obviously structurally controlled. So now we're starting to see the structures that actually control the location of the ore deposits. So what do these rocks look like? Well, the most distinctive are the carbonate turbidites, which are locally called calp. And this is a dramatic shift from the shallow marine carbonates in the Corsaean to these deeper water turbidites. And this indicates the development of local structurally controlled basins. And you can see on the left in outcrop what these rocks look like. So variable bed thickness with the massive limestone portion of the bed standing proud, and in between erosion of the shaly bits, which we can see in the drill core image in the lower right. At the same time, we had deposition of shallow water limestones, so shelf limestones. And we know this at the same time from doing lots of micropaleontology to actually get micro critters in both rock types that tell us they're the same age. We also have the oolites here, which we can actually find in the lower right is that dark unit within Walsrosian limestone. So that's Walsrosian limestone that had been uplifted during the structural event, karstified, and then down dropped, and the oolites are now filling in a cavity, a karst cavity, in the Walsrosian limestone. So clearly, things have been going up and down during the Chattean. If we move to the next stage up, the Arundian, the patterns in the Arundian are really very similar to those of the Chattean. We have still volcanism continuing. We have both the shallow and the deep water, and the ore deposits forming at this time also are forming on these structural zones of the small subbasins. Okay, so that gets us into the structural history. Ireland during the Lower Carboniferous has a period of extension, and in the mid-Corsaean, sort of the time of the ABL and the Walsrosian, we start to get many extensional segmented fault arrays. And these are centered on the middle part of the basin, which we call the Iapetus suture zone, which is this zone of contact between Avalonia to the south, Laurentian to the north, and it's essentially where the plates are coming together. And it's essentially a strike step zone. There are subtle formation thickness changes at first in these units, but as we get into the Chattean, we see clear differences in the thickness of the units, showing us these normal faults are moving more and more as we get into the Chattean and then the Arundian. And we know this now from seismic work that's been done in the country, so we have lots of seismic lines showing us where these faults are. The faults have produced narrow horsts and grabens, and along strike, faults in these extensional features can become multi-strand or join up into single structures, and they can have curvilinear traces. And we can see that in the lower right, where you can see the different ways these faults interact and come together or stay separate, right? And so there's a lot of complexity along this fault array. We have continued faulting in the lower Visayan Arundian, and essentially in the Arundian, probably the maximum amount of extension. The bottom falls out of these basins, and approximately along the trend of the Iapetus suture zone. So that's where the axis of that suture zone is where most of the structural activity has occurred, and that's where most of the ore deposits are. Okay, the sedimentary pattern is dominated by major faults and the development of the subbasins, the Dublin Basin in the northeast and the Shannon Trough in the southwest. And we have this facies mosaic of the different types of carbonate rocks, which are showing us what's deep and what's shallow. Now, what happens after the Arundian is basically there's very little extension. We have sea level rise, and we cover all these rocks with later relatively shallow water carbonate rocks, and eventually it actually grades into a deltaic system with sediment coming from the north and covering them. So we bury the ore hosting lithologies and the structures that controlled those deposits, which are no longer active, which means they can't be seen at the level of these higher depositional units. So we can see that the sedimentary faults formed during the Chattean and the Arundian do in fact control where the ore deposits are. So in the lower right, you can see the white there are the normal faults in the Lachine system, and they're an overlapping array of normal faults. And the darker zones to the north, above those faults, are the ore bodies at Lachine, of which there's multiple. Largest off on the left, the main zone. And the bulbous one in the middle is the Derry Kern, and then the bog zones. But you can see that the deposits actually are at points of what it turns out are maximum throw along each of those normal faults. And they're sort of spaced regularly, which is a way that we can actually then do exploration looking for these things. So one of the things that's happened since I originally worked here and found Lachine back in the 1990s is that the companies have come in and done lots of seismic exploration in the country. And so we have a number of seismic lines that we can use to help find faults. And this map is a current map showing where we know the location of many of these faults, even ones that are now covered by later carbonates where the faults don't actually penetrate that high. And we're seeing faults in two different colors. Those that are south dipping are in red. They're mainly in the north. Those that are north dipping are in blue, and those are mainly in the south. And then the width of the line of the fault actually is keyed to the amount of throw it has. So we can actually see how big the faults are. Now this map isn't complete. There's areas we don't have seismic. And so, this isn't a complete geologic map, but it start to being an idea of what the structural boundary and structural architecture of this area really is. And what this is actually doing is essentially implicating what's happening in the basement. Remember that the contact between the two cratonic areas beneath us is roughly northeast-southwest, and we see that in the regional geophysics. So on the left, we have the Bouguer anomaly, the gravity, and you can see a whole series of northeast-southwest trending highs and lows. And superimposed on that in the blue lines are the faults that we've been able to map from seismic. And you can see that most of those faults actually correspond quite closely to that basement geophysical architecture. Some cross it, but many of them are parallel. On the right, it's a different area of Ireland. This is what's called the Rathdowney Trend, where the Lachine deposit is. This is an EM system that's been flown. And even though it's harder to see, in gross terms, again, the structural architecture mirrors what we think we see in the basement. So structures in the basement are being mirrored higher in the stratigraphy during the extensional event in the Carboniferous. After this extensional event and after sedimentation, the area was influenced by collision of the plate to the south, which brought more sediments from magmatic arcs further to the south and caused an orogenic event, the Variscan Fold and Thrust Belt in southern Ireland. There are obviously a number of thrust faults in the south, but through most of the Irish ore field, we don't have big thrust faults, but many of the normal faults, especially those that were oriented properly, underwent reverse motion. And so in many ore deposits, our original normal faults have been reactivated and moved, and we get reverse or thrust type movement along them. And in red at the bottom there is one of the ore bodies at Lachine, where you can see the ore body has actually been pushed up over the other one. So the original normal fault has been reactivated and gone from normal movement to reverse movement. Paragenetic sequence of alteration and mineralization in the deposits. So the general characteristics in these deposits are, in terms of the mineral paragenetic sequence, we go from early pre-mineral hydrothermal dolomite formation, sometimes succeeded by hydrothermal iron formation, so deposition of silica plus hematite, then going to early pyrite, then sphalerite, then mixed sulfides, sphalerite, galena, pyrite, and copper-silver sulfides. Sulfide textures are complex. They're dominated by massive fine-grained wall rock replacements and coliform banded Vugg-Fehler replacement. The alteration associated with these deposits, mineralization is commonly, but not always, preceded by dolomization, and there may be a silicification and deposition of iron oxides or iron formation prior to sulfide precipitation as well. We do know the age of the mineralization relative to the host rocks, based on a variety of geochronological methods, and I'll get into that in a little bit later. But essentially, mineralization happened within about 0 to 10 million years of the deposition of the host rocks, so relatively early. The generalized sequence here in a fish diagram shows this as well. Hydrothermal carbonates precipitated before the sulfides, but continuing right through and to after sulfide formation. Early iron formation, or silica plus iron oxide, followed by barite, followed by pyrite, followed by sphalerite, then galena, and the copper sulfides. Pre-ore dolomization is important. This is in the Navan group, and much of the host rock in the Navan group was dolomitized differentially. Different layers were dolomitized, others not, and this actually affected the permeability of how hydrothermal fluids then move through that package later. The same with the Walsortian. Some deposits showed no dolomization, such as the Tina deposit and Belinalac, another one. And in these deposits, the mineralization actually extends completely through the Walsortian limestone near to the fault, which was guiding fluids up. Other deposits, such as Lachine, Galmoy, and silver mines, the Walsortian limestone has been dolomitized, either partially or completely, and we get more stratiform ore bodies that extend out along the base of the Walsortian, and the dolomization is actually allowing for more permeability and allowing the fluids to go lateral. So again, that's the early hydrothermal dolomization. Then we look at iron formation. So it's important that some deposits like Tina, where you can see in the upper two left-hand slides, the reddish there is the iron formation itself, quite thick, and there it's underground as well, over a meter thick there. At silver mines, it's much thinner, but still there, very similar red rock, and in a similar stratigraphic position. And at Lachine, it was even smaller, but again, the same materials there preserved basically in breccias and inside zones that were later replaced by sulfides. This just shows what some of the Lachine material looks like in thin section. So it really is red iron formation looking rock. And you can see from the mineralogy, the pink there, you can see on the far one, the silica, that's all quartz. And the iron, the blue there, it's mainly hematite, but there can be bits of magnetite as well. We also see this at the Navan deposit, but again, it's relatively small. So at the top left, you see that reddish material, and in the one below it, you can see it's just forming sort of on one little bed there, up in the UDL, which is the rocks above the deposit. And again, you can see a fragment of this material sitting in a breccia at the Navan deposit. So it's something that's actually come off and rolled into a conglomerate in a normal fault scarp. Okay, after that we get into the main period of mineralization with early barite, pyrite, and then the sphalerite galena. So this is the zinc-lead mineralization, what we're actually looking for. And the age of this, we can tell a couple of ways. Geology is probably one of the very best ways. Above the giant Navan deposit, we have rocks called the upper dark limestones, or UDL at Navan. And within those rocks at Navan, we have super abundant, finely banded, massive pyrite in the carbonate turbidites. And whether this is actually syngenetic itself or diagenetic, forming or during early diagenesis, it's irrelevant. What we can see in the image in the middle there is a conglomerate which contains many, many clasts of the massive pyrite in a matrix that also has pyrite and carbonate. So clearly this material was forming more or less at the sediment seawater interface and was then being eroded during deposition and during active faulting along these normal faults. We have replacement mineralization by zinc-lead. So at Navan in the upper left, you see both oolites and the foram replaced by the brown sphalerite. And on the right, which is reflected light from Lachine, We have another foraminifera, which is being replaced by pyrite, sphalerite, and then overgrown in this case by chalcopyrite. In terms of replacement, we also have cavity fill, so the rocks being replaced, but also cavities forming and then sulfides forming in those cavities. Here we have a contact between dolomite above, so rocks that were dolomitized prior to mineralization, and rocks below that are still limestone. A stockwork of veins has come up, of sulfide veins, primarily sphalerite, coming up to that contact, and then fluids running out along the contact because the dolomite was less permeable and less reactive. And in those zones, you can see at the upper left-hand corner, sort of a white area there, which I've taken a blow up of the slab of rock. And these are stalactites of primarily sphalerite coming down. This was an area where fluid pressure actually formed a cavity or a jack-up between the two units, and sulfides were able to precipitate in those voids, forming these stalactitic growths. Replacement at Lachine in the Walsortian, just showing how it's progressive. So on the left, we have a thin section of Walsortian limestone being cut by that vertical vein, which is largely sphalerite with dolomite in the interior. As we go into the middle there, you can see sort of parts of that rock replaced by the brown material, which is mainly sphalerite, but some pyrite as well. And then on the right side, you see a rock that's now massive sulfide composed of pyrite and sphalerite. And so it still has the same textures as the original Walsortian, those odd sort of bulbous things, which are called stromatactus, but it's now 100% sulfide. And we can look at this in thin section too. This is regionally dolomitized Walsortian at Lachine. So on the upper left, just a little bit of sphalerite in intergranular porosity. Going to the right, you see that sphalerite eating away the dolomite. Then coming back down to the left, more sphalerite. And then on the final one on the lower right, the whole rock now has been converted to sphalerite. There's general agreement that the bulk of the ore stage sulfides in the Irish ore field formed by these sorts of replacement processes of the host carbonates, and it replaced both limestone and dolostone. However, the depths at which the replacement took place are often not well constrained, but the indications are that it's from the relatively near surface, things we saw at Navan, to probably several hundred meters, things we see at places like Lachine. In terms of the age of mineralization, I'll get to a minute why we know it's relatively near surface because of the sulfur isotopic composition. But we've also done a series of geological or geochronological techniques in Ireland, and we have a range of ages from 360 down to 334, and most of the ages are actually falling sort of in the 340 range. And so you can see the age of the host rocks there in the red bar. And then the large bar there is the age of most of the mineralization dates. So most of the mineralization is forming sort of within, 5 to 8 million years of what we think the age of the host rocks is. So relatively close to the age of the host rocks. So what's necessary to form an Irish ore deposit, or really any ore deposit? We need a couple of things. We need to get the elements of interest, the source of the metals, and the source of the sulfur. We need to transport those materials in fluids and along fluid pathways. We need a means to concentrate or trap the metals. And then we need the energy to drive the system. And all these are at least in part chemical processes. So we need to think chemically here to give us the parameters of what's possible. So in terms of source, work over the last 35 to 40 years indicates that the metals in the Irish ore deposits were ultimately sourced from the lower Paleozoic rocks, and in fact the data suggests the metals are coming essentially from directly beneath the deposits. And the main evidence that's been used, or probably the best evidence, are lead isotopes, where we have lead isotopes clearly from galenas in the deposits, but we also have done a lot to collect galenas from veins in the basement underneath the deposits and throughout the country. And those isotopic values are plotted up. We get a, not surprisingly, northeast-southwest zoning of the lead, which is reflecting the basement rocks and their ages and their types. And the lead in the ore deposits actually has exactly the same trend. So it's clear that there is a relationship between lead in the basement and lead in the ore deposits above the basement. In terms of the sulfur, we can actually fingerprint it very well as 2. So barite is present in many of the deposits. Look at the source of sulfur for that barite. It usually comes between plus 17 and plus 27 or so. So it's heavy. But that's the same value as the value of sulfate in carboniferous seawater of the age of the host rocks. So the sulfate going into the barite is essentially coming from coexisting carboniferous seawater. Now, the sulfur in the sulfides has a wide range. The values range from about plus 15, so not that far from the barite or this carboniferous seawater, all the way down to almost minus 50, right? And those lower values, certainly below minus 10, those are values we get from bacteriogenic reduction of seawater sulfate. So we must have bacteria actually taking seawater sulfite in the near the seafloor, essentially, or near seafloor, and reducing that sulfur through bacterial activity, and that resulting sulfide then being pulled down into the ore deposits and fixed. But we also have sulfur shown there in the lower Paleozoic vein-hosted veins from Fontaine, and that is, sulfur that's in sulfides in the basement. And you can see that it's roughly between 0 and plus 10. And we have hydrothermal sulfur in the ore deposits as well that have similar values. But as you'll see, most of those sulfides that show that value are in very particular places in the ore deposit. So at silver mines, one of the deposits of wall sorption, the upper graph actually shows the stratiform ores. So barite, which forms a large stratiform body, has values of about plus 15 to about plus 21. So that's the carboniferous seawater. But most of the sulfides in the stratiform sulfide bodies go from 0 down to about minus 37. Okay? So that is dominantly bacteriogenic sulfur. When I come into zones that are immediately adjacent to the normal faults and fault-hosted breccias, and those were mined as well, those sulfides, the barite in them shows the same values, carboniferous seawater, but the sulfides tend to be heavier, basically centered on 0. So there must be hydrothermal sulfur, or sulfur in the hydrothermal fluid, which is roughly at 0 per mil, coming up into the deposits, and then mixing with a large reservoir of bacteriogenic sulfur, which is forming then the major stratiform ore bodies. We see the same at Lachine, where again the deep sulfur gets as heavy as plus 18. Just below the ore deposit, it goes plus 15 to plus 5. And in the ore deposit itself, we instantly go into sulfur that's sort of minus 20, minus 30 on the fringes, and up above the ore deposit, where presumably the bacteriogenic sulfur is descending from the seawater, down as light as minus 43. So bacteriogenic sulfur there. But the story in detail is very, very complicated. This is work that was published from Galmoy. You see this coliform banded sphalerite here in the image with 2 traverses where they were able to do in situ sulfur isotopic analyses. And what you see in traverse 1, for instance, going from bottom to top, it goes from highly negative, minus 20, up to 0, then drops down to minus 18 or so, bounces around, and then comes back up to plus 7, and then goes back negative again. So what we're seeing is mixing of the deep hydrothermal fluid, which has sulfur values of, +1 or maybe heavier, with the bacteriogenic sulfur, which has values down to -40, and they're mixing in a whole series of very complex pulses. And this mixing is what's actually forming the Irish ore deposits. So this gets us to transport of fluids. The sulfur isotopic data tells us there were two fluids: a sulfur poor, both sulfate and sulfide, metal-bearing hydrothermal fluid, and a sulfide-rich, bacteriogenic, probably cooler fluid, which carried most of the sulfur. And we actually look at the compositions of these two fluids using fluid inclusions. Whoops. So if I look at the deposits that are hosted in the Walsortian, where I have a lot of my data from, you can see there's multiple different deposits there, but they overall form a trend going from a high value, highest temperatures of roughly sort of 240 in Tina, down to lower values of 100 and a Galvoy and silver mines, somewhere in the middle. In terms of salinities, they're varying from about 10 weight percent NaCl equivalent up to about 24. Okay, so it's range of values, but temperatures of say 240 to 100 and salinities of 10 to 25. At Navan, which is to the north, we also see a variation. This is in time now. So the early fluids at Navan, I have a maximum value of about 170, 180, whereas the later fluids are coming down into the sort of 120 degree range. And the salinities are going from low initial salinities, 5 to 10 per mil, down to, in the later fluids, up to as high as 25 weight percent NaCl equivalent. When I look at the basement veins, these are plotted on top of the Walsortian deposits. What you can see is they actually show values that are relatively similar to the Walsortian deposits. So maximum temperatures of about 240, 230. Minimum temperatures here below 100. Salinities of 10 to roughly 22 weight percent equivalent. So a good overlap, right, between what we're seeing in the basement veins and what we're seeing in the ore deposits in the Walsortian themselves. So the general model for forming these deposits is inflow of a metal-rich fluid, relatively high temperature, that being somewhere around 200, coming up structures, going into the stratigraphically lowest clean non-argillaceous carbonate rock where the fluid can escape and get into that rock, mixing with fluids that are coming down from the top from carboniferous seawater that are, because of bacterial activity, reducing the seawater sulfite to sulfide, precipitating, in that case, on top of the deposits, pyrite, which has isotopically quite low values in terms of their sulfur, and then getting down as far where they can mix with the actual metal-rich fluid so they can form sphalerite, galena, chalcopyrite, etc., with mixed values. Some quite low, some quite high, some going back and forth, depending on how the mixing is occurring. So what are the pathways? The hydrothermal fluids, clearly derived from seawater, transited through the basement, we know that because of the lead isotopes, and overlying the basement, the old red sandstone, before reaching the near surface and then mixing in the rock column, but with carboniferous seawater. And all of the Irish deposits are located along or immediately adjacent to normal faults, and the offset on those faults ranges between 100 meters to over a kilometer. Most of the deposits, as I showed you earlier from Lachine, are actually located adjacent to points of maximum throw along individual normal faults. And where we have studied these faults in detail in some of the mines, such as Lachine and Navan, the normal faults appear to form en-echelon ramp and relay patterns, which are indicative of oblique slip or some sort of strike slip movement. The metal zoning patterns in several of the deposits indicate that the structural conduits for mineralization change through time. So we actually see different mineral assemblages, and they overprint one another, but they may move along the fault zones at different paragenetic stages. And so it's showing us that in fact, this is a dynamic system in time with fault movement changing, and therefore where fluids actually can access through the faults changing as well. So the extensional fault fluid pathways are the same faults that control the carbonate facies mosaic. And so understanding the sedimentology and the stratigraphy locally helps us to actually pinpoint where we want to go along these fault systems to look for deposits. And the overall pattern of faulting suggests northwest or north-south directed extension, and that's relatively minor, sort of 10%, but with a component of dextral shear, which is why we open up these northeast-southwest trending grabens and horse between the two main basins, the Dublin Basin and the Shannon Trough. The trap. How do we actually precipitate the sulfides? You can do this in mineral systems with either two ways. It can be a physical trap, sort of like in the oil business where we trap hydrocarbons, or it can be a chemical trap where the fluids react with something. They cool down in temperature. They mix with another fluid, which they do in the Irish systems. Or they're acidic and they react with carbonates and change their pH. So all these are possibilities. At Navan, we have both physical and chemical trap. So the Navan deposit actually sits on a major horst. And on the cross-section, we can see this. Here's the horst. It went up so much that it had a major, what they call degradation surface, or an unconformity, which stripped off much of the Carboniferous section before it was then overfilled with carbonate turbidites. And the red there are the ore deposits in the pale beds of the Navan group. And you can see they're trapped up dip by that unconformity surface, which forms an impermeable layer. So these are essentially physical anticlinal traps, very similar to what an oil field would look like. But they're also chemical traps. So this is in a small scale now. There's the dolomite, which is relatively impermeable. Below is limestone, which is chemically more reactive. And so the sulfides are actually forming in the limestone where they can react with that, as opposed to the dolomite, which is less reactive to this slightly acidic ore fluid. And this just shows some of the ways that you can do that. And I'll let you look at your own time. You can see this, but we have multiple chemical reactions that can actually take place in a system like this. The same thing happens in the Walsorson-hosted deposits. Again, part of the trap is physical, up adjacent to these faults, coming into the more dolomitized Walsorson at Silver Mines and Lachine, and then being able to go out laterally along the base of that unit, which is more permeable because of the dolomization. Whereas at Tina, where the dolomization didn't happen, the mineralization escapes all the way through the Walsorson limestone and reacts with that limestone, replacing the limestone with sulfide. In the ones where we do have dolomite first, Lachine, Silver Mines, Galmoy, we often form, at least in Ireland, what we call black matrix, which is a dolomization of Walsorson limestone or dolomite. And this is basically this unit here. It's a rock which has undergone multiple periods of dolomization. The black there in the matrix is a combination of fine-grained sulfides, but also actually porosity. So very, very small pores, which trap the light and make it dark color. And as you can see in the cartoon in the lower left, we basically have mesosulfide, which is moving out through the dolomite, black dolomite breccia, the BMB as they call it. And this is what we see in drill core. So on the left is the BMB, the black matrix breccia, with a little bit of pyrite in the matrix. The next one over, you can see there's more pyrite and sphalerite, primarily the matrix. Then we replace the matrix with sulfides. And if we continue, We replaced not only the matrix, but the clasts themselves, and that rock is now almost essentially all sphalerite, galena, and pyrite. This is what it looked like underground. And so below is the black matrix breccia. You can see a lot of sulfide, especially at the top, which is pyrite. And then above that, the black matrix breccia with sulfides in the interstices, in the matrix, which disappear as one goes upwards. So what's the energy to drive this? We need something that drives fluids. And this has been a mystery, and to be honest, still is. We're still working on this, and we don't really know. The relatively low degree of extension during the Corsaean to Arundian, and the relatively thin sedimentary succession, especially at the time of mineralization, do not provide an obvious means to drive extensive fluid flow. So one of the things that may be happening is, are we contributing direct heat? So enhanced heat flow is something we've talked about for many years here as driving fluid flow. We know there was excessive heat in the Irish Midlands from things like conidite alteration indices and vitrinite reflectance. We know that the temperatures were anomalous before the Variscan orogeny, which then heated everything up again. So there was heat being contributed here, but we're not sure how. And we have other kinds of evidence besides the CAIs and the vitrinite. We know this from helium isotope work, from osmium isotope work, and interestingly enough, from lower crustal xenoliths, which are carried up in the basalts. And we have dates on when they're actually being heated up, and the dates are almost exactly the same as the age of mineralization. So in the south of the country, we have an area that may be showing us more what is happening more generally. In the Limerick syncline, which is near the Shannon Trough, just south of it, we have numerous alkali basalt, marked diatremes, lava flows, etc., and placed into a shallow submarine environment at essentially the same time and later than deposition of the Walsortian. We know from doing chemistry on these rocks that these magmas were sourced by partial melting of an enriched and metasomatized mantle, and these things were erupted in a within-plate continental extensional environment. So what we see at Stone Park, which is one of the prospects there, is that's the section. The blue is the Walsortian. The black are different breccias, some of which contain sulfides, and we have these maars that cut right across. So clearly later than the mineralization in this particular instance, but how much later? We also see areas where again, here's dikes that cross-cut the breccias, and the red is the ore zone. But we see clasts of some of the igneous material also in some of these mineralization-related breccias. So some of it must have been there before the mineralization. So the igneous activity is taking place essentially before, during, and after the mineralizing event, at least in this area. So the Limerick syncline may be important about what it's sort of telling us about what may be happening over much of the area of the Irish Midlands. We think that ponding of magma at the base of the crust, combined with the extension that we know, could have promoted relatively high heat flow and helped ensure the structural permeability of the rocks and the basement and enhance fluid circulation. So this sort of igneous activity probably is key. And then the final thing I just want to talk to you about is most people talking about Ireland wouldn't be talking about copper. And since 1970, I mean, everybody in Ireland's really been looking for zinc, and Ireland is a major zinc producer. But Ireland was once known primarily for copper, and this would be 18th century and before, with copper production going all the way back to the Neolithic. We did have one modern copper mine here, Gort Drum, which was hosted in the carbonate rocks. So I've been arguing for many years that we should go back to looking for copper. And copper sulfides are present in virtually every one of the Irish ore deposits, with the exception of the biggest, which is Navan, which is also the furthest north. Most of the copper in these deposits is present in or adjacent to the feeder zones, and these copper-rich zones almost always have enhanced silver, and many may contain other minerals, nickel. The Gort Drum mine, which operated between 1967 and 1975, had reserves of 3.6 million tons at almost 1.2% copper, 25 grams silver. And they were hosted in the Ballystine limestone, the lower limestone shales. So not in the traditional host rocks that we've been exploring the last number of years, which is the Walsortian. And here's just some numbers. But the very last one there, Ballywire, this is a press release that came out about a week ago, a little over a week ago, May 8th. And you can see they released recent results, 12 meters at 2.3% copper, 560 grams per ton silver, including 6.4 meters at 3.72% copper. And this is in the base of the Walsortian. So the actual interval that was mined at Gort Drum has not been tested yet at Bally. We suspect there'll be a there should be a nice deposit sitting underneath even these high-grade results. So Gort Drum is the old mine, and we've been working on that again just to look at it. You can see it's also along a fault system here. Mineralization is hosted in the lower section, in the lower limestone shales, and in the base of the Ballystine Formation. And when we put it together, we can see again it's an overlapping system of normal faults, so a ramp relay system. The ore deposits here, rather than being stratiform, are essentially sort of in a tube-like ore body near fault intersections, and there's several of those along the fault zone. So it has a different geometry than the deposits that most people have been looking for the last couple of years. And there may be more. This is the Tobermollog, Stone Park, and Plan View. The red are the sulfide zones. The brown or the gray here is dolomitized brushes as a halo. And I put in at the same scale the size of the Gort Drum deposit, which I suspect is a feeder zone for something like this. Major faults have not yet been found at Tobermollog or Stone Park, but they're probably going to be on the order of what the Gort Drum deposit is. And so none of the holes targeting this ore deposit have drilled down to the level of the Gort Drum yet, mainly because they haven't seen where the major structures would be to actually target such a thing. But I suspect there is potential moving forward. And then we want to step back and look at the whole country again. So if you were here, where would you explore? Well, it's clear that this zone going through the middle of the country, which is called the Iapetus Suture Zone between the Laurentia to the north and Avalonia to the south, this strike-slip zone of compression of a whole series of island arcs and basins. This is where all the action is. The different lines there are different places where geologists over the years have actually put the line. Rather than actually putting a line, I suspect it is in fact a distributed shear zone, and it's really the entire package of faults here, which is the Iapetus zone, and that makes sense. Where along that zone then should you actually be looking? Well, it turns out, the biggest deposits here at Navan where the zone's coming in sort of almost east-west and then turning abruptly to the southwest. And we have another zone here with the Shannon Trough coming over and doing a similar bend, and this happens to be where the Pallas Tobermollog deposit is. So I would suggest that these fault bends are actually areas where probably we're breaking up the lower basement and allowing for more circulation of hydrothermal fluids in that fractured basement. That may be why that's where the big ore deposits are. That's one of the things we need to do going forward, is actually understand the basement better and see if we can map out geophysically zones of leaching and zones of fracturing so we can actually find the areas which may be the best ones for larger deposits. We don't know how to do that yet, but we're working on technologies to help us with that. And if I step back even further, right? This is now the early Carboniferous, but after the period of lead zinc mineralization in Ireland. You can see the encroaching Hercynian fold belt there to the south, and this is the Carboniferous carbonate platform, which extends from Ireland right across into Germany and extends the other way to the west into the maritime provinces in Canada. There's normal faults associated right along this whole thing, and the normal faults are giving us the fluid pathways. I think the fluids are actually focused into the Irish Midlands due to the fact that we have these high areas both to the east, the Bremont Massif, and to the west, just offshore. And the Irish Midlands actually is a place where fluids could, and marine waters first, as aggression, and then regionally fluids being expelled would move in that direction. And remember, underneath the carbonates is a fluvial package, which should be really good for transmitting fluid. So even though southern England and, well, northern England and Scotland have exactly the same sorts of rocks that Ireland does, the same facies mosaics, they record the extension, they have volcanism, but we haven't found any major deposits there. I suspect it's because they didn't have access to fluids coming from the southern part. They had to actually go through the Irish area before they could have got there. And that's why the ore deposits are here. Out here in Belgium, there were deposits there. Interestingly, that's at sort of the end of this massif. And so this may be another area where fluids actually were able to push northwards more easily. There's a whole series of things that we here in Ireland are trying to do now to move forward with exploration. I'll leave this to you to read, but, confidence to look for new ideas. We have a lack of drilling in many areas, even around some of the known deposits in the mines. We need to understand the basement better, and we're working towards that. We now know that many of the faults that are mineralized actually don't extend to the surface because they're covered by post-mineral carbonate rocks, which weren't faulted. And so, we really do need the seismics to figure out where these faults are. We have a huge amount of new work that's happened both regionally and in detail, which needs to be improved. We can do a lot better with logging now, especially with the scanning technologies we have. We have huge amounts of geochemical data now, the original soil geochemistry and rocks from the deposits, which we can actually improve and use AI to come up with new vectors towards new deposits. And we have a whole bunch of lithologic and alteration studies, which we've been working on, which again should be giving us new vectors. So with that, I'd just like to conclude that, just like where Peru and Ecuador and Chile and Colombia to your north have huge deposits to be found. You're an elephant country in all those countries. Here in Ireland, even though we're much smaller, we probably still have some elephants to find too. And there'll be both lead zinc and copper. And it's going to be your generation that's going to find them, so let's get out and do it. Thank you very much.
Thank you, Dr. Hitzman. It was a truly informative lecture, and yeah, you highlighted the geological complexity of Irish type deposit. It is really new for us. We haven't seen this kind of deposit before. Thank you for the lecture. So we have some questions in the chat. We can go through them. Okay. Marco asks, thank you, Dr. Hitzman, for the presentation. I was wondering, what role do carbonate platforms play in the formation of Irish type singlet deposits?
So the platforms, it's really looking at the different kinds of carbonate facies and trying to understand where the different facies abut one another, usually because of structures. So a carbonate platform, we want to understand where the edge of it is, where it goes into a basin. Hope that helps.
Okay. Another question from Jorge. Excellent talk. Which geophysical methods have proven most effective when exploring for Irish type mineral deposits?
That's a good question. To be honest, seismic has been the one that's actually found the most. So seismic allows us to actually really define the stratigraphy and pinpoint the structures. So if I had to say anything, I'd say seismic would be our best technology.
Okay. Another question from Alfredo. How does these compressive traps work? This is the mineralization
So it's
process?
not so much a compressive trap, well, a physical trap. So yes, compressive in the sense that it's an anticline. And so we're forming something where fluids can come in and get stuck. At Navan, the anticline's there, and because it has this unique unconformity surface, which is very impermeable, that allows the fluids to come up and get trapped against it. So yeah, I guess that is compression in that way. Yep.
Okay. Another question from Luis. Although we are discussing metallic singlet deposits in the Dublin area, did they also encounter any petroleum accumulation given the extensional
Right.
regime and basin
Excellent
conditions?
question. The honest answer is no. So uh, Ireland doesn't have that good of a source rock. So it doesn't look like the Irish systems generated much hydrocarbon. There's a small bit of bitumen in some of the deposits, but the Irish systems just don't seem to have generated a lot of hydrocarbon early on. Nope.
Okay. There are two questions left. Which mining method, open pit or underground, would be most suitable for their exploitation, given the deposit's depth, morphology,
Right.
and economic considerations?
Most of the deposits in Ireland have been underground. We had open pits at silver mines for the Ballynoe barite deposit, and Gortrum was mined open pit, and Tina was mined open pit. So both have been used. But at this point, just from a social point of view, I'd say underground is by far the easiest to permit, and people are more used to it here. It has less probably disruption socially. So I would think in future most mines will be underground.
Okay. Another question from Manuel. Good evening, Dr. Hitzman. Thank you for your time. I have a question regarding geochemistry. What geochemical pathfinders are considered most diagnostic when targeting
Yep,
Irish-type
great
deposits?
question. Zinc and lead. Right? I mean, it sounds crazy. We're looking for zinc and lead, but zinc zinc actually is, disperses quite widely. And so it's by far the best pathfinder element to find zinc deposits. Just look for zinc. We use a whole suite of different elements,
Mm,
but zinc has been by far the one that works the best.
okay. Another from Alfredo. Does the isotopic geochemical signature of mineral paragenetic ores confirm the sea-water interactions during the hydrothermal
Yeah, it
process?
does. So everything we've done isotopically actually confirms that the carboniferous seawater is the main fluid that's operating in the system, both into the basement to leach the metal and coming down from the surface, bringing with it the sulfur. So yeah, carboniferous seawater looks like it's it.
Okay. And the last one from Emilio. Why some sediment-hosted deposits are enriched in molybdenum, cobalt, like Kipushi type?
Okay, so those are quite different. Um, we're also working on those here at University College Dublin, at Capucci itself, and some others down there. They're a very different system. They're formed not at the same time as the host rocks, much later. They're formed from very salty systems, very highly saline, possibly from higher temperature, um, and probably from very different source rocks. So, we're getting metals from a much different place than we are in the copper belt. So they're fundamentally quite different systems.
Okay, just to finish, those were
Okay.
all the questions. I want to share my screen.
Thank you very much. Yeah, yeah, yeah. Thanks.
Can you see it? Yeah. Okay, Dr. Hitzman, on behalf of our SEG student chapter, we sincerely thank you for sharing your expertise with us today. We truly appreciate your time in contributing to our academic formation. And as a token of our gratitude, we would like to present this certificate of appreciation, which reflects our deep respect for your contribution to our chapter. Once again, thank you for being with us today, and we look forward to staying in touch
Sounds.
and hope to welcome you again in the future. Thank you,
Thank
Dr.
you very
Hitzman,
much.
and thank
Thanks
you
everybody
all
for
for being here.
listening. And yep, if there's anything I can do going forward, let me know. Good luck for the student chapter there in Quito. Cheers.
Thank you, Dr. Hitzman. See you next time. Good luck in Dublin.